Hello and welcome back to another episode of Getting into GiG-04. Welcome back, Sydney.
Hello.
And after a wonderful weekend, we are back to our stats program here, which now looks like this if you run it. So we see the repository directory itself, how many commits we have, and the most recent commit message, episode 3. And now we are thinking about what to do next. Which means Sydney is thinking about what to do next because I'm just the hands.
Yeah, I mean, that's pretty cool already. We can count commits. We can actually look into different commits and find out more information about those, like the message. So next step, maybe can we find out the overall size of the repository, everything that's in it, basically.
Okay. Then let me refactor this a bit. Wow, that was slow. Amazing. I don't know what's going on here. So that's our commit here. And if you want to venture into the tree or what kind of files there are in our repository, then we have to get the commits tree. And that's here. Let's see if that still works, by the way. Oh yeah, see, I thought so. Sorry, you don't see that actually.
There you go.
Now you see it. Let me move a few windows around. Okay, that's better. Okay, because this is why we do this, right? We try to do things and then we run into problems because stuff doesn't work anymore. Temporary value is freed at the end of the statement and borrowed later. Consider using a let binding to create a longer lived value. Okay. So toCommit creates a commit ref. And a commit ref, you see it borrows data. And if it borrows data, you always have to ask yourself, where does it borrow data from? Where's that data held? And maybe we can see it here. You see the data here is held or is coming from self data. And that's an interior, it's borrowed through a cell, which to us can just be a borrow. And that borrow lives in, maybe that wasn't quite clear yet, lives in our easy object. So that's an easy here. This is why we have a ref cell and not just a normal borrow. Okay. And this is where it comes from, that object. So this is the, let's say the power, but also the curse of Git repository, the high level, because it hides a lot of details from you that you don't have to deal with anymore, like where's the data stored, but you still have to let it live long enough because this is Rust and there's not necessarily shared ownership everywhere. I mean, there's a form of shared ownership here, that's for sure, but it's not shared for each, it's not shared in each low-level object that we might get. Because what we do in the end is we decode the data buffer that is in this object into a commit, but that data buffer has to be held and that's in the object itself. So yeah, let's just call it object, good enough. But object ref is more precise because it does reference a data buffer that lives elsewhere.
So you need to store it into a variable to let Rust know this should live a little bit longer, otherwise it just drops it immediately after the call.
Yes. And Rust has this, look at this, Rust obviously was doing something smart here, right? Because this is the same issue technically. Like this gets created and then theory it just drops right away, but somehow it lives longer. And that's because Rust probably optimizes for this case and says, okay, if you do this kind of thing, I keep it alive for you. So you don't have to do this binding all the time. But now that you do more, you have to deal with the binding yourself. Fair enough. So if you build this now, it does build and it does run. Okay, cool. Now let's get the data. Now that commit is a commit ref, which is this low-level commit object that lives in Git object, the Git object plumbing crate. And this really is just an object. There's nothing special about it. You can access all the data that is contained in one of these commits. What we are interested in is the tree. But as you can see here, the tree itself, let me move this over. The tree is actually just literally a string. Like this is parsed from the commit, because commits themselves, they just have these hex encoded SHA-1 hashes. So yeah, with that we can't really do much. I mean, we're inside the computer, inside the machine here. The good thing is, one of the very nice things in Rust, look at that now. It still looks like the same, but it's not. So you are able to access the same name as a function if there is one, or as a field if there is one. And there's no conflict at all. These are in their own namespaces. And this is what Gidoxide does a lot. The original you get through the field, and through the function you get the converted version. So this decodes an object ID from the hexadecimal value that we saw before. And this implements display. So if you display that one, it displays as hex again. So it looks like it's the same, but it's not.
I see.
Right. So if you do this, it's 40. And I actually don't know if I implement lang here, but maybe I do. I do not. But as slice, I think I do. So you see this has 20 bytes only, so it's decoded. All right. And that's that. So we want the tree object. And ideally, I would want to get an object again like before, right? So like here we have an ID, and now we just get the object for that, then we convert it to a tree, and then we should be able to iterate that tree somehow. Why not? And unfortunately, there doesn't seem to be an object method here. This is not available on object ID. Yeah, why's that? What's the difference? Oh, look, we have different types here. That's an OID. That is an easy OID again, which is basically an owned object ID plus access to the underlying handle, the easy handle, which is a handle to a repository. So this is how that extra comfort comes into life. Whenever these are bound to a handle, they can do additional stuff, because that has all the state that they would need to access the object database, to access caches and so on. And this is just an ordinary object ID, which lacks the handle. So it would be nice if you could attach a handle, huh? So maybe we can. So where is our handle? It's called repo here. That's fine. So we say repo, make it easy, too easy. And then we just keep using this handle that has all the information it needs for our purposes. And we should be able to it's repo to attach this like that. And now we can do all the fancy things on what comes out of there. So you see an object ID plus a handle equals an OID, an easy OID. Makes sense. And now we should be able to get the object. Yeah, let's just do this to see how it works. Huh? So we just get there step by step. Does that work? Let's see. Oh, it failed. See. Borrow state, borrow mud error. Oh my god. Yeah. So what is intuitive did not work intuitively. That's a bit sad. We don't see much here. We just see the debug print because we don't have any how here. But yeah, even if you would see text, yeah, I just say what it would say if you would see text here. It said it wanted to borrow a shared buffer for storing the object data in, similarly to what it did here, because we have commit data. But it couldn't borrow mutably that buffer because it is already borrowed. Where is it borrowed? Here. This object ref, look, whenever I call object here, I effectively use that shared buffer. Shared because each of these handles has one buffer.
Okay, yeah.
And it's in a ref cell, so it's using interior mutability. Even though we call functions that are not technically mutable, internally they are. So this is a trick you play so that Rust actually allows you to do that, because Rust is the thing that would prevent you from having something mutable twice. But then you can't really do much, so this is why you work around this like that. This makes it much more convenient, but also means each handle can only have one object at the same time. So we can't have the commit and the tree at the same time. How limited is that? Yeah, it really is. It is a limitation that you probably run into at least once when using Git Oxide. And that's something that isn't the case, for example, in libgit2 or git2. So it's something kind of special, especially once you want to traverse the tree or the repository structure. You have to always be aware that there is this one shared buffer. And now we have to find ways around that, right?
One shared buffer per handle or per repository?
Per handle. Okay. So what's the simplest, the most straightforward way you can think of that we could use to work around this?
You open another repo, essentially.
Yeah.
You start from scratch.
You could start from scratch. You could say repo, I mean, you probably could keep that repo and then make another too easy, because this doesn't consume the repository anymore. It just makes puts a new handle into existence. Or, like, something that I can imagine might be simpler. Tree repo. Can we clone this? No? Okay. So now that worked. So we just cloned the handle, and now we have another set of buffers and another object we can keep alive at the same time.
That's just the handle. That's not the entire. Yeah, that makes sense.
Yes. So it uses shared state internally to still link to the same repository, reuse shared resources, but also have your own thread local resources. And of course, each thread can have multiple of these for different purposes, like this.
That's, I mean, doesn't clone imply something else? Like you would say that it has its own resources, that it wouldn't be shared, but in this case, you're saying it still links to the same one. Isn't that kind of a bit counterintuitive?
Maybe, but also clone does not say it's standalone. Because you can also have an arc, right? You can have shared ownership of stuff, arc RC, that's shared ownership. And once you clone these, they're still referring to the same item that is owned, but now you have a handle to that. And the same thing, it's called clone. One way to kind of make this less counterintuitive with arcs or RCs is to write it like this. I think we have done that at some point. But you don't do that here. So I take that as very valuable feedback that says maybe there could be something that is, you know, more obvious, duplicate or something like that, so that it's clear that it's another cheap copy of a handle that, yeah. Or
I mean, it's a naming thing, right? If you know, then you know, and it's totally fine. But I think usually clone maybe means something else.
Yeah. Interestingly, I didn't see it like this with my personal experience, let's say, but I might also be blind towards this because, yeah, you know, you want another one, you clone it. Because to me, once you know what a handle is, then if it lets you clone it, you just expect it to be efficient. I mean, this is what GiG-04 promises. So, but maybe there's a better name for it. Even though clone will always work, of course, because it has to. That's how these things are going to be used. They will be cloned around into multiple threads, has to. But there might be a more obvious name for that. Yeah, great point. There might be another way, because we are already done with that commit, right? We only want the tree. So we could also just have the tree ID here, use the commit, then we drop it. And now we use the original repository, because that frees the buffer reference that is in there. Obviously, after we also remove that one. So you see now we drop the thing that refers to that thing, and now we drop that thing that refers to that thing. So we have a chain of 3 links here. We have a commit that points to the object ref, which points to the buffer inside of our handle. Let's call it handle. That's also a bit more obvious. And that should work just as well, but it doesn't let me compile. Commit. Oh yeah, right. I'm dropping this, but I'm still trying to access that. This is why we kept the tree ID earlier. So we now get the data out, copy the data that you're interested in. That's the technique, so to say. And now it works just as before. And that's another way to do it. And with this is probably the one, I mean, it's probably not super awesome to do it like this. Maybe you can, I don't know if that works, because they are self-referential now. I don't think that will work, but maybe it can. Yeah, see. So it's kind of a little self-referential structure here. We try to store something that references something else inside of one structure, self-referential, which Rust will not allow. This did not compile, by the way, because of this. Because it tries to move stuff around that is referring to each other. So now we have to drop that separately, which doesn't look super awesome, I must admit. So yeah, okay. Maybe just have a second handle for that so that you can just use that.
Yeah, that would be cleaner in this case, I think. It's, yeah. I mean, this also makes sense, but I feel like the other way is maybe a bit more readable, I guess.
All right, then handle 2, for the lack of a better name. We clone this, and we can keep that. And then we have commit tree, attach handle 2, like before. Okay. And now we can get the object and do all the high-level stuff through that, if you wanted to. Let's see if there is anything interesting that it allows us to do, because right now we didn't yet actually have a tree, right? This is just playing around. Can we get trees here? We can get a tree, ref. Is that an easy? That is an easy tree, ref. Not too bad. I don't know what that can do. Data, it only has lookup path implemented here. And lookup path does not really do much for us. Yeah, it doesn't do what we want. We want to see the entries that are in a tree, and then we want to recurse into more entries, so to say.
Mm-hmm.
So is that, so now it's interesting. Is that the same tree ref? I think it is, huh? It's also an easy tree. Yeah. Interesting. So how do I get a normal tree through this one, I wonder?
You mentioned that you can convert the easy back usually to its to the full version, basically.
The thing is, now we just want to get the tree, and then we convert it back and forth to kind of, you know, it's like, ooh, it's making a lot of loops. And maybe it's easy because we don't get anything from that high level right now, I think. And this is also, I hope, consider a strength of, you know, let's say all these things that you usually want to do, eventually you will implement them on the high level, so that you just say, hey, give me an object, convert to a tree, and then you do tree traverse, and you visit all the elements in there in some order, and it's all just there for you. You know, that's the vision. Right now we don't have that. Now we drop one level down, which you can also do, and it's very powerful, because that's the actual data structures that you then have. You just have to deal with a few things yourself, but much less now than before. So let's see. We have handle 2. There we have objects, which is our object database or object store. And here we should be able to find a tree. Look at that. Or even a tree iterator if you want to. Or try find. Okay, try find, that allows the thing to not exist, but we know it should exist. So we just say find plus conversion. So find tree finds us a tree that is fully decoded, and errors if it's not there or if it can't be decoded. So that seems quite useful. Or this one here, find tree iter. Okay. And that now takes an object ID, which shall be commit tree, and it takes a buffer. Okay. So you see, now we basically bypass the buffering that is happening here and have to specify our own buffer, which might be useful later when we actually don't know how many buffers we need to do that kind of stuff that we want. We don't want to run into these borrow issues. So that's something to consider. But we should also be able to find an object directly. Like so far, we always use this to object thing. Maybe you can just do this directly too. Yeah, it's the same thing. So apparently handle also implements the same find thing, find object. it's also my first time to actually try it like this, you know, from a very user perspective outside of tests or something like that, where you're very focused on one thing, but just try to get something done and see how that feels, especially with code completion and so on. So that seems like the highest level method that we have here, find object. And that gives us an object graph again. So it's kind of the same thing as attach an ID and then call object, you see? So now we find the object directly. And then we can, it probably just did the same thing. Yes, we did, but a bit differently. So this is a less object-oriented approach, isn't it? Now we call a method with the ID instead of binding the ID to make that smart, and then you add, you say, hey, you can now give me the object of yourself because you know everything. All right, so now we are where we were before. We can now convert this into objects here, which again is, this is again the kind of tree ref that we didn't want to have because it doesn't give us anything, or I didn't notice it. So what can this thing do? Because we want to have the actual tree. Where are the entries, right? Here's just bare data. Can I get entries for this? Into tree. So now we have a tree. It doesn't have an entries function because it didn't implement that yet. And it's kind of superfluous, I guess, because you should just use a normal tree. So can this thing do, or give us a normal tree object? Find ID from data, no. Or from ID and data. No, it does not. It does not give us, it does not give us any of that. Yeah, it doesn't.
I mean, that's probably something that any easy handle should be able to do, right? So that you can drop down into the actual full data structure, then you can work with it
yes.
in a more deeper level.
Yes, I would expect that. I mean, the thing we do with commit object ref becomes a commit, that becomes a normal commit here. But in case of, so that's an inconsistency that we just discovered here, because we have this kind of stupid but usable commit object here. But for trees of all of the items here, for trees, we do have a smart object that is bound to the handle, but that doesn't really give us the actual tree that we wanted to. But it does have conversions here. So this conversion, maybe this can also be triggered somehow. But I of all people should know, huh? If that's there or not, but I don't. Okay. Interesting. Maybe that's, since we are 30 minutes in already and kind of struggling with something very simple, maybe that shows that this really should be improved. You know, you can always create an object manually, which is maybe something we do for lack of any other way. Let's try that. Like, we find an object. I don't know what object can do either, because it's kind of hard to see if there's no screen real estate. This is what you probably, this is probably when you pop open the documentation of Git repository, and then you can figure it out there. This is what I would do. Have the docs ready. And find object. So what can you do? Your object ref. Yeah, into tree, we already know that. Detach to commit. And what about conversions? Trait. From object ref for object. Okay, so that's the owned version. That is also an easy object, which is probably not very interesting, can't do much. Here we also see a bunch of methods, but not exactly what we want. It's a bit strange because I recall I did that. I did that already. I did that in Smart Release. Most definitely. So how did I do that there? So we have commands that deal with traversal maybe. Oh no, not that one. Oh, okay. Think. It's about the Git history where it does access trees. Please give me some tree. And look up the path there. Create refs. It's so hard to find if you barely see anything. It's not working for me anymore. Tree ref iter here. There we go. Okay. So as you can see, it's done a bit differently here, but it fetches all the data for actual trees, and then it just creates a tree ref iter by hand from the bytes directly. And I guess this is what, I mean, this is basically working around a missing API. Here I didn't miss any API because I was caching data anyway as byte buffers, and then you just wrap an iterator around that and say, here, this is your entries, iterate them. And that's exactly probably what we have to do, because a tree is not much more than a bunch of entries, which is a list of things. And right now we have no nicer way of doing this. So maybe there's also some interesting outcome. We run into missing API bits and pieces and figure out ways to make that nicer. Because for now, all we can do is find the object. We assume it's a tree. We can convert it into a tree if we want to, why not? Have a tree ref. And this does the type check for us. So now we know it's a tree, but it didn't actually do any decoding or something. It's just data that we have that contains the tree itself.
Yeah. And this entries function would then do exactly what you did in the smart release, right? You would take the data and then build an iterator from that, basically.
Yes. This is also usually how I see Git repository. I just use it as Git, and then from there, it's the hub through which you can access everything else. So Git, OBJs, tree ref iter from bytes. Hey. So that does exist, that's nice. And then we have tree ref, and there's this public data that we can just reference here. Now we have entries. And these entries, that's just, you know, because we now have an iterator, we can just call next on one. Maybe that's something. Does it have debug printing? Now we can see the first item of a tree. Yay, that was easy. Cargo.cargo. Okay, now we're getting somewhere. I think that's a good point to rest and think, because that now has to be done more elaborately to traverse that tree structure, to count items recursively and obtain data recursively. Like, how big is that thing? How big is .cargo? Was that by any chance in here? Does it contain the size? How does an entry look like now that we are here? It's a okay, so this thing is a tree. Tree is a directory. It's called .cargo. and it has this object. This object refers to it, and that's all. That's all that Git stores for its tree entries. So in order to get the size of this thing, well, it's a directory, so I guess it doesn't count for size. Nth1, let's get the first item. Now we have blob, editor config, but the same thing here. So you see, we would now have to retrieve the data to actually get the size of it.
But the tree has the entire, like everything is contained in there basically. So it's basically we're just iterating through this tree and then its directories, getting all of the objects.
Yeah.
And then you can actually count the size.
Recursively going through that data structure essentially. And then you can count the things, yes. I think that's a nice programming exercise that we leave for the next episode. I don't think that till then there will be any nicer API, but that's okay. That's also something to improve on, and then we adjust this example here and make it better and nicer as the APIs manifest. I think that's how it could be done. So
yeah, that sounds good. It's like the playground, and we find everything that's could be useful and that's needed, and then in the background it'll get implemented.
Yes. Somebody can do that at some point. Okay, thanks a lot, and see you for the next episode. Bye-bye.
Bye-bye.